Thanks, Doug. Yeah, if you guys looking for a take-home message from the next half an hour is whatever Doug just said. And if you didn't pay attention, I'm awesome. Yeah. So this talk, I'm just going to talk about what we think going on as far as Avalanche, dry slab Avalanche release, and how we verify those understanding, and we think we have a decent idea of what's going on. And then a couple practical implications from those findings. And before I start, this presentation is accumulation of a couple of recent publications and some stuff that haven't been published yet. Before I start, I want to acknowledge the authors on those publications. And Carl Birkeland is here if you guys have questions at the end of the talk. So avalanches start on a micro scale with small cracks between the snow grain. And when a large enough external load is applied to the snowpack, it initiates a crack. If the crack propagates under the external load to a critical size, the stress at the crack tips due to the slab, the load of the slab itself, exceeds the resistance of the weak layer for fracturing. Then the system becomes what we call dynamic, and a self-sustained crack propagation starts. We call this stage dynamic crack propagation. If the crack propagates over a large enough section of the slope, the slab breaks away from its surrounding. The snowpack, the surrounding snowpack, the crown of flax, the starch wall are formed, and the snow movement starts. And then there's not that much we know about dynamic crack propagation. In this talk, we talk about some stuff we know about it. So why do we care about dynamic crack propagation? Well, I care, and this is mine 15 minutes of fame, so you have to put up with me for now. And as far as we know, the size of an avalanche is dictated by the dynamic crack propagation. And we may be able to leverage some of those properties of dynamic crack propagation to improve our risk reduction. So until recently, we had two competing crack propagation theories, the shear propagation mode and the pure anti-crack mode. The problem is that according to the shear mode, avalanches are almost impossible to trigger on slope flatter than 35 degrees. And we just heard this morning that a lot of people triggered WUMPs last winter. And according to collapse mode, avalanches are almost impossible to trigger on slopes steeper than 45 degrees. So it appears that neither one of those models will give us a complete picture of high dry slab avalanche release. One way to get a better handle on crack propagation is through measuring the crack speed. And as you expect, people have measured crack speed, have measured weak layer crack speed as property of the propagation for a wee while now. Johnson, Jamieson, and Stewart measure crack speed from WUMPs. And many others have measured crack speed from PSTs of various size, with the result ranging between mid-teens to mid-40s meters per second, which align with the collapse mode. In 2014, Dave Henry, Carl Birkeland, and I presented a data set of crack speed estimates from avalanche videos. The method we used was simple. We just noted the time and location where an avalanche was triggered, the time and place where cracks on the snow surface started to appear, and drove the speed from the distance between the trigger point to the surface crack and the time it took those cracks to appear. The challenge with this approach lies with its failure to account for the time delay between the moment a weak layer crack reaches the boundary of the release area and the subsequent appearance of cracks on the snow surface. So the avalanche needs to be really big, above 200 meters for that to be really reliable and not minimum size limit, minimum speed limit. Nevertheless, those measurements reveal unexpected results. About 30% of those estimates were above 100 meters per second and well above the previous measurement from WUMPs and PSTs, and above the speed prediction of both anti-crack and shear mode. So it appears that the process we see on flat terrain, PSTs, and full-scale avalanches are not always the same. Recently, computer modeling of avalanche release has become increasingly more accurate. Those models accurately predict measurement from PST tests. Another example is this realistic-looking model-generated video of an avalanche that Joan Goom created. And how realistic it is suggests that he's doing something right. The increase in model accuracy and the scale mismatch between column test measurement and slope size avalanches led Joan and his group to model a large column test to see how cracks propagate in a weak layer. In this simulation, the PSTs are on 30-meter slope, 30-meter columns. So this is really a squish picture of those columns. The top column is on flat terrain. The bottom is on 30-degree slope. Everything else is similar. Clearly, the slope is making a big difference in how cracks along the weak layer propagate. We call this fast propagating super shear crack propagation. We call it super shear because the weak layer propagate in a shear mode. The fracture in the weak layer propagate in a shear mode, and it is very fast. And not because it's not bounded by the wave speed of the slab. Let's look at where the crack propagation between the two columns diverge. It seems to be somewhere around 5 meters from where the crack initiation started. We call this point supercritical crack length, and as you can see, it's well past the typical column test size. Therefore, there is no wonder that we did not see the transition between slow collapse and fast propagating super shear regime in a field test. This is a 2D illustration of the slope size avalanche. On the left is what it looks like along the weak layer. On the right, what the avalanche looks like on the snow surface. As you can see, when a large enough crack is initiated in the weak layer, it propagates in the same speed in all directions. Once it reaches the supercritical crack length, it starts to rapidly propagate up and down the slope in a super shear mode, and cross-slope crack propagation speeds remain limited to the collapse wave. So how do we know that the crack mode changes from mixed mode anti-crack to super shear after it reaches supercritical crack length? The reality is that we don't know exactly what happened when avalanche release. However, our model predicts specific behavior. If we confirm those behavior, we can be somewhat confident that our model described the avalanche formation reasonably well. In our case, fast super shear crack propagation up and down the slope and slower cross-slope propagation. So, life is simple. We only need to develop a method to measure weak layer crack speed of real avalanches in the different directions. Here I present a new method to measure crack speed from avalanche videos that does not rely on visible crack on snow surface. For example, this video of a small avalanche experiment from SLF. It would be nice if you could see it in a more insightful way, maybe something like this. As it turns out, sometimes we can. We just saw the same video after applying a method known as Eulerian video magnification to amplify tiny movement in the snow surface. For this study, we assumed that these snow surface movements are indication of the fracturing weak layer underneath it, and therefore allow us to detect weak layer crack propagation on a slope scale from real avalanches. We built on the idea of Eulerian video magnification to develop a detection algorithm. We call it Eulerian video detection, or I'm going to use EVD in this talk. Essentially, what we do is tracking the pixel intensity or brightness of the pixel in every location on the slope during the duration of the video. For example, let's follow the average pixel intensity in the green rectangle. On the upper right in blue is the pixel intensity, and in red is the pixel intensity signal after filtering out the noise. The bottom chart is the derivative of the red signals. What we're looking for are the steep changes in the red line, which in this case is marked in the red rectangle at the lower plot. Just as around the video, the dark vertical line traversing the chart corresponds to the time within the video. Now, if we apply the process everywhere on the slope and mark each location where we detect strong changes in pixel intensity, we can track the surface movement as a proxy of the crack propagation tips as they progress across the slope. To see if our assumption of the snow surface movement are good proxy to crack propagation, we use the EVD to detect both snow surface movement and the weak layer fracture along the sidewall. And we were very excited to see that the snow surface movement and the weak layer crack tip track well together. Just what we can, we also use the EVD on location outside the avalanche boundary, and we find no drastic pixel intensity changes like within the avalanche zone. Now that we feel somewhat confident, we can start using the EVD on slightly more exciting avalanches. This deep slab avalanche was triggered in 2019 in Wallace, Switzerland. Luckily, the snowboarder is a phenomenal rider and managed to ride it out. Don't try this at home. Using EVD revealed that the weak layer crack propagation quickly advanced in a downslope direction and in slower speed across slope direction. Only much later in the process, we start seeing crack appearing on the snow surface. We also look at this video from Alaska. And the sequence is the same: fast down propagation down the slope, and slower cross slope propagation with surface crack becoming visible much later in the process. We look at this video from Juneau, Alaska. And again, fast down slope crack propagation and slower cross slope propagation. In total, we had 49 speed estimates from 6 videos. Now, if graphs are not your thing, feel free to doze up for a few minutes, and rest assured we'll be back on the solid ground of moving snow shortly. For the rest of you, this plot shows the speed estimate, these estimates, with time from initiation on the x-axis and the distance on the y-axis. The arrows represent the direction of propagation, and the black for hard slab, gray for soft slab. It appears that our estimates start to diverge into 2 main groups after 25 meters, the slope direction group and the cross slope group. We use the average speed of for each direction in each avalanche to calculate the crack speed in up-down slope direction and cross slope direction. The dashed line represents the mean speeds in slope and cross slope direction. The steeper the line, the higher the speed. The cross slope speeds are in line with speed measurement from PST and WUMFs. The up-down slope direction speeds are much faster and in line with the upper end measurement of Hamrys. This pattern confirms the transition from collapse to super shear crack propagation mode that we talked about it earlier in this presentation. So other than giving me an excuse to watch videos of avalanches at work, what are the practical implications? Avalanche size is typically dictated by the terrain and spatial variability of the snowpack. However, can crack speed indicate the size of an avalanche with these limitations? We did not find clear correlation between cross-slope crack speed propagation and distance. We suspect that, among other things, the terrain prevented long-distance crack propagation regardless of propagation speed. That being said, we have strong indication that propagation speed on flat terrain correlates well with propagation distance. How about in the slope direction? An initial look-see of our data suggests that there is a positive correlation between the crack speed and propagation distance. These are encouraging results, especially when we look at speed estimates from large slopes, marked here in red, when there is less terrain limitation in the slope direction. So it appears that better understanding of dynamic crack propagation can help us forecast in avalanche size. Putting together a few of those concepts we just discussed here, we can start thinking about different ways to go about avalanche reduction methods. For example, avalanche defense structures. Avalanche defense structures are designed to anchor the snowpack to the slope and stop avalanches from running altogether. Therefore, they need to be robust and densely placed across the slope. In other words, they're very expensive. Now, if we can protect infrastructure by preventing avalanches from reaching them rather than stopping them altogether, we may be able to design smaller, more affordable avalanche defense structure by splitting large avalanches into several small avalanches, and therefore reducing the overall run-out distance. For example, Stanley. Stanley is an avalanche path that keeps me from sleeping several times in winter. It has several GASX units for avalanche mitigation marked in circles. And depending on the portion of the start zone that avalanche, debris cleaning can be up to 6 hours long. And that's when the governor gets a phone call. The relatively slow cross-slope crack propagation suggests that slope traverse and crack are relatively easy to arrest. So what if instead, anchoring the snowpack to the slope, we create a special variability in slab thickness to arrest or delay weak layer crack propagation across the start zone? Since cracks propagate slower across the slope, those structures will completely stop the section of the start zone from avalanching or create a delay between smaller avalanche, preventing them from reaching the road. This is an idea that we currently explore, and if it works, it can reduce installation cost and maintenance of avalanche defense structures. We did numerical simulation with the proposed defense structure. In this video, the structures stop one side of the slope from avalanching and split the large avalanche into smaller avalanches with release delay large enough to prevent them from merging and producing a larger avalanche flow on the other side of the slope. So far, it looks promising. But there are a few more things we need to figure out. So to summarize, numerous studies propose distinct crack propagation regime on flat terrain cross slope and up and down slope direction. Nevertheless, prior to this point, we did not have field observation to substantiate this concept. These speed estimates provide the first field observation to support this idea. And on this optimistic note, I want to acknowledge the people that helped me with this presentation, and thank you for your attention. Yeah.
In some of your videos, the propagation appears very discontinuous. What do you think's going on there?
I just didn't pick it up in the video, the threshold changes in between of pixel intensity.
Just lighting effects, maybe?
That's what I would think. Could be just the propagation path was going around, but I would guess it's just the algorithm didn't pick it up. Yeah.
What considerations did you have with those avalanche defense structures? I noticed you had them going upslope rather than cross slope, and were they on concavities or convexities, or what considerations did you have there?
So we need to do a lot more modeling to actually see what's the best shape, how much infrastructure we need to put on a slope, on specific slope. But the idea is it's not uncommon for us to see a slope that has those really shallow, small sub-ridges on it. And especially early in the season, you will see that avalanche is just not going to propagate all the way across. It's just going to stop, run in sections. So the idea is just to kind of highlight it and create it more extreme. The idea with structure that's basically going in a slope direction, they don't really have to absorb the brunt of the weight of the snow or stop avalanches. So at least in theory, it needs to be a much lighter structure. Does that answer your question? Or?
Yeah, totally. Nature-inspired design, and then it's easier to build something up and down versus side to side.
Well, we'll know that after we actually try it. Yep.
You said that currently we essentially don't have a good way through tests to test for super shear because they're not like long enough, so it doesn't transition to that. Do you think that that is important to try and figure out if we should be testing for that, or is that actually like, do we kind of cover it with just the collapse?
No, I think it's important because what we want to know, and there is some work is done by SLF in SLF. They're actually trying to have those small avalanche experiment, and they're having 12-meter long PSTs going down the slope, and they have cameras looking at the weak layer in different places. So there is some work. It looked like they got some really initial results last winter. They're not quite there yet, and they actually tried to look at the weak layer to see how it breaks. And they get funding for it, so it's obviously important enough.
Yeah, I guess from like a forecasting perspective, I was trying to think like if that's something we should be trying to figure out how to test for super shear, or in your mind?
So it transitioned to super shear after, we say 3 to 5 meters. You won't get very far on your field day if you're going to try to do those columns. So I think it's important to understand what's going on and anticipate that, but to trigger avalanche, I think as far as we know, it's more important to see if you actually manage to create that mixed mode anti-crack collapse, and then to start something going on by itself. And Carl, you probably have deeper thought about it than me.
Well, I mean, you have to remember too that in order for it to transition to super shear, you need to be on a slope. And so, because you need to get that snow to start to move, and then that's what helps drive the thing forward. So not only would you have to do a really long column, you'd have to make sure that you're on a steep slope when you did that column. So yeah, it's like Ron was saying. I mean, I think I don't know. I mean, there's one way to test for that, and that's with an explosive. Really,
Or someone no one else like. No, Ed, what are you guys thinking? What are you guys thinking about?
Oh, about it with regard to super shear?
Yeah.
What I want to say. Yeah, it's not. I think it's an interesting concept. I think that it probably is valid. I think some of the, whether or not you got the pressure wave and the shear wave, or it's driving it all makes sense. I don't know if that's what your question to.
Yeah, but it's not necessarily going to help us forecasting for.
Oh, I don't know, and I don't know, about cross shear, cross slope and vertical. Kind of half retired here, so.
Ron, do you have any sense on if different slope properties drive when that transition happens? And
Yes.
do you definitely need to have that transition to get an avalanche, or can you have one that doesn't go through to super shear?
Well, in theory, it can keep on going in mixed mode anti-crack across the slope, and it's probably happened. But actually, it should be, if it slides, it should be steep enough. But it depends on the weak layer. How weak is the weak layer? The slab stiffness. Stiffer slab need longer supercritical crack length, and we find out it's really important the collapse magnitude. So the bigger the collapse magnitude, the smaller is the supercritical crack length.
Do you have any thought if some of that could be what we're seeing with the times we're getting whoops but not avalanches? It doesn't go through that transition. Would that make sense?
Maybe it doesn't go to that transition. I don't. Yeah, I don't have a good answer for that. I'm just as baffled as anyone else by the. Seeing tons of collapse and no avalanches. Yeah.
It seems like you, aside from the one where you're wearing like snowshoes and stepping on the snow, most of your videos were like starting the avalanche from the top, and that's the speed of that traveling down. Have you done any videos to see like if the speed of it going upslope versus downslope, if one's faster than the other?
We have one video and we didn't see any, at least that one video, we didn't see any big difference between the climbing up or going down.
Thanks, Ron.
All right.